Our viewers, in this video we will solve problem 8.25 from the book Heat Transfer J.P.Holman from 10 chapters of the heat transfer book. So here is the statement of the problem. Two parallel discs 60 centimeter in diameters are separated by a distance of 15 centimeter and completely surrounded by a large enclosure at 100 centigrade. Properties of the surfaces are T1, emissivities of the plate surface T1 and T2, and its emissivity is 0.5. What is the net radiant heat transfer with each surface? Okay, so let me write the given data. So the diameter of the discs D1 and D2, that is given, and it is 60 centimeter. So convert into meter, just divide with 100, so you will get 0.6 meter. Okay, so the distance between the disc, that is x, and it is 15 centimeter. You can say 0.15 meter. Temperature is T1 of the plate, that is 540 centigrade. 540 centigrade convert into Kelvin, just add 273 with it, so you will get its value, that is 813 Kelvin. Then T2, and it is 300 centigrade. Just add 273 with it to convert into kelvins, and you will get, that is 513.73 Kelvin. So the emissivity of the plate 1, that is 0.7, and the emissivity of the plate 2, that is 0.5. so here it is. And the temperatures of the room, that is enclosed in it, so that is T3, and it is 100 centigrade. Convert that into kelvins, and you will get 373 Kelvin. So let's say this is the disc 1, this is disc 1, and this is the disc 2. Both the discs have the same diameters, and the distance between these two discs, that is x. Okay, remember, whenever there is a radiations occurs between two same diameter discs, so its shape factor can be calculated from this graph. So how you calculate the shape factors for these two equal coaxial discs? Okay, so this is the disc 1, that is at temperatures of T1, and this is higher temperatures, this is the lower temperatures, T2. So this is the room, that is enclosed in a room. Let's say enclosed in a room. This area is very large, so its surface resistance will be approximately 0, so we will not consider its surface resistance. So this is T, and its temperature is 373 Kelvin. So now first we will write the important parameters that we need. Area A1 is equal to A2 pi by 4 d square. So pi by 4, what is d? That is 0.6 square. So you will get area A1, A2, because this is the same disk, so you will get its value, that is 0.28. So now I will draw the radiation network diagram of these three bodies. So first, the heat transfer, this is EB1. Then talking about this plate, so the heat transfers is occur through its surface resistance, then its radiosity J1, then again the space resistance, and then will heat heat transfer reach to the radiosity of the body 2, J2, and then emissivity of the body EB2. So EB1 has surface resistance, also EB2 have the surface resistance, but surface resistance for EB3 will not be considered because its surface area is very large, so its surface resistance will be approximately equal to 0. Now J1 heat transfer will occur to the room. This is J3, and this J3 will be equal to EB3. Then surface resistance, and then J3 heat transfer that is occur from body 2 to the room. So this surface resistance of the EB1 that is equal to 1 minus emissivity 1 divided by area 1 emissivity 1. And this is equal to 1 divided by shape vector 1 to 2 and area 1. And this is the surface resistance, that is 1 minus emissivity 2 divided by area 2 and emissivity 2. This is the again space resistance between J2 and J3, so it will be equal to 1 divided by F23 into area A2. And again this is J1 to J3, this is surface space resistance, so that will be equal to 1 divided by shape vector 1 to 3 and area 1. So area 1 and area 2 is determined from this formula. Now look at the shape vector, how we will calculate it. Look at this graph. The ratio of d by x is equal to, what is d? That is 0.6 divided by its x, that is 0.15. So you will get its value, that is so here this value and the axis is 4. So if you move upside, this 4 value coincide with this curve at this point, so you will get the corresponding shape vector, that is 0.6. So our shape vector f1 to 2, that is 0.6. From this graph and from this, with the help of this ratio, we can find the shape vector between f of 1 to f of 2 between these two disks. Now according to summation rules of the shape vector f of 1 1 plus f of 1 1 2 plus f of 1 2 3 will be equal to 1. But in this case the shape vectors f of 1 1, so this disk cannot see itself, so it will be 0 and its value is 0.6. So f of 2 3 will be equal to 1 minus 0.6, and that is 0.4. So shape vector f of 1 2, with the help of graph from summation rule, we get f shape vector for f of 3, that is 0.4. A1 f of 1 3 is equal to A2 f of 2 3. This area is equal, so it will be cancelled out, so it means that f of 1 3 is also equal to f of 2 3, and that is 0.4. So all kind of shape vector has been determined so far, and that is our requirement to solve and to find the net heat transfers. Next is to find the resistance. So 1 minus is infinity 2 divided by A2 emissivity 2. So I'm quickly writing its value. Okay, so all the resistance that you can see in this radiation network diagram, I'm writing here. So for the ease of convenience, I'm finding its value separately. So by putting the values, you will get the resistance, surface resistance of the plate 1, that is now perform the node analysis on this J1 node and then J2 nodes to find the required equation to find its value, because without these values you cannot find the heat transfer of Q1 and Q2. So all the heat current that is entering the J1's analysis, look at here. So this heat transfer is occurred from EB1 to J1, that is equal to EB1 minus J1 divided by 1 minus E1 divided by A1 E1 plus now heat transfer from this J1 to J2, that will be equal to J2 minus J1 divided by 1 over F of 1 to area 1 plus, so there is 3 junctions 1 2 3, so there will be 3 turns for this node, and the sum of these heat current entering to this node J1 must be equal to 0. So the heat current that is entering from J3, that is J3 minus J1 divided by, remember J3 means EB3, so we will also need to find the EB3 first, and that is equal to 1 divided by F1 of 3 A1, and it is equal to 0. So here the EB1, EB3 value is also unknown, so we will first calculate that. Also we will calculate the EB2 value, that is also used further. So it is EB1, it will be equal to sigma T1 to the power 4, T1 to the power this sigma, that is 5.67 multiplied by 10 to the power minus 8 multiplied by T1, that is 813 power 4, and you will get its value, that is 24,767. Similarly EB2, so I'm writing these equations on this side. To multiply each terms of these equations with the value, multiply it 1.5, 1.6, 5.89, 8.84, with the value you will get 1.5. So I'm simplifying this equation, so multiply these two denominators with each other, so you will get the value, that is 79.04. So now multiply this 79.04 with each terms of this equation. So after multiplication you will get the equations in the form of like this. So after simplifications, these equations, you will get the first equations for these two unknown, that is 13.4 J2 minus 74.47 J1 is equal to minus 130,000 and 130,115. This is, let's say, equation 1. Now we will perform the node analysis on the J2. So we will write the equations for J2 now. So it will be equal to AB2 minus J2 divided by its surface resistance, that is minus 1 over emissivity 2 divided by area 2 emissivity 2 plus the heat transfer from this room to the J2, that is J3 minus J2. J3 means EB3. I have written here because it is equal, that is equal to 1 divided by F23 into area 2 and plus this heat transfer to this node from the body 1, that is J1 minus J2 divided by 1 over F of 1 to area 1. Okay, so now take these equations and enters the value. Now I'm entering the value directly, so you will get that is 600. So here you will got another equations for the node 2. Now simplify this. Similarly, the previous one equation we have simplified, so the final answers you will get, that is for this simplified versions of equation, that is minus 104.18 J2 plus 31.2 J1 is equal to minus 34,138.45 and say it's equation 2. Now solve these two equations simultaneously on the calculators, and then you will get the value of J1 and J2. So the J1 value is 19,090 watt per meter square and the J2 value is 9,000 watt per meter square. Now to find the heat transfer by the body 1, that is equal to Q, it is really equal to AB1 minus J1 divided by its resistance or surface resistance. So just put the values because all the things are known, that is, so you will get heat transfer by the body 1, that is 3745 watt. Now heat transfer by body 2, it will be equal to AB2 minus J2 divided by its surface resistance, and you will get that is minus 817 watt. And these are all final answers. I hope you understand. If still have any confusion, you can ask. Thank you so much.